Welcome to the fourth video of this series on preparation for the TEAS test. Today, I want to talk about states of matter, classifications of matter, and their phase changes. Matter from as long as I can remember, grade school on, has been defined as anything that occupies space and has mass. Anything that's not matter, of course, is classified as energy. There are many states in the universe that can be applied to matter. We're only going to be concerned with the three most common under conditions in which we live: solids, liquids, and gases. When we try to make the connection between what we can observe, the macroscopic world, and what's actually happening in the invisible or the microscopic world, the connection is such that we need to understand why solids look and behave the way they do, liquids similarly, and gases behave the way they do. And the best place to begin is to look at their structure. Solids have a regular structure, and the molecules or the atoms, as the case may be, are locked in place. They cannot move. We say that they cannot translate from one place to another. Now, while they're there, they can vibrate, and they do vibrate, but they're still in their relative positions. That's what allows solids to have a definite shape, and it holds them to a definite volume as well. So a solid can hold its shape independent of any container, and its volume is constant for any given temperature. If we add energy, then we can move a solid into a liquid phase. And the liquid phase has made one slight adjustment to the arrangement of atoms or molecules. And that is, we've added energy to the solid so that the vibrations have increased to the point where the attractive forces between the molecules are now loosened enough for the molecules to slide past one another. That's for that reason, liquids tend to have a constant volume, but not a definite shape. They have a definite volume, but not a definite shape. So they must be held within a container. Gases, on the other hand, we've added enough energy to the liquid so that we completely break the bonds, the forces that hold those molecules, even in a close proximity where they slide past one another. But now we've added so much energy that they're completely independent particles. And that's what we're showing in this far right-hand side. Steam is the gas of water. And what the artists are trying to show there is that these water molecules are moving very fast. Right? You can see these traces behind the molecules. They're moving fast, and there's lots of space between them. In fact, there's more space between them than we can show in this video. And it all depends upon how much energy we add, usually in the form of heat. We're raising the temperature of the material, and as we do that, we make the transition from solid to liquid to gas. And we already mentioned that solids are rigid. They have a definite volume and a definite shape. Liquids have a definite volume but not a definite shape, and they must assume the shape of the container, while gases have no fixed volume and no fixed shape. In other words, they take the shape of the container no matter how big it is, and the volume of the container as well. Now, I want to talk about mixtures, but first we have to understand what a pure substance is. A pure substance is any type of matter that has uniform properties throughout, and also it consists of only one type of particle, one type of atom, one type of molecule, whichever the case may be. It could be an element, it could be some compound, right? And so that defines a pure substance, as well as we cannot separate uh, anything we've identified as a pure substance cannot be separated by physical means into simpler pure substances. We've got down to the pure substance. That's as far as you can go by physical means, such as uh, boiling off part of the substance and leaving behind some other substance. It doesn't work that way. Once you get that pure substance boiling, all of it goes. Or you filter, or use some other physical separation uh, procedure. Now, the key to this physical process is ask yourself the question: is the substance, after the application of the process, is it the same identity as it was before? If it's the same identity, then the substance is not only pure, but there has been no chemical change applied to that substance. Only physical changes. And physical changes never change the identity of the substance. Examples: gold would be an element, right? Pure substance. Table salt is a pure substance, only it's a compound of sodium and chlorine. Sugar, pure sugar, that you sprinkle on your cereal or put in your tea or coffee, is a pure substance. It's based upon the molecular structure of carbon, hydrogen, and oxygen together in a particular ratio and a structure. But it's still pure. The only way we can break it apart is to break bonds, and we can't do that by physical means. Oxygen is another element. Water, a compound. Now that we've got pure substances, we can make mixtures with them. We can add two or more substances together to make a mixture. And the major substance, that is the one that is the highest percentage, we call it the solvent. And there can only be one solvent. Anything else we add in there in a lesser amount than the solvent is the solute. Right? And that can be many. Now, I'm going to talk about that in more detail in a subsequent video, so I'm not going to labor that point at the moment. If the mixture is homogeneous, that is, if the parts that we put together, the pure substances, are equally distributed throughout, then we have a homogeneous mixture, which we also call a solution. If, on the other hand, we try to mix two substances together and they don't mix uniformly, then that's a heterogeneous mixture, such as sand and water. If you try to mix sand and water, it looks like it's homogeneous when you're mixing it, but once you stop mixing it, the sand starts to settle out, so you get differential composition throughout. That's a heterogeneous mixture. Here's an example of a problem. And remember what I said in a previous video: when you're faced with a problem, you say, what is the question? This one's easy. The question is right there in front of you, staring you in the face. Which of the following is a homogeneous mixture out of these 5 selections? Well, let's start at the end. Which is a mixture? Is pure water a mixture? No. So you can disregard that one. How about copper metal? No, that's not a mixture either. That's a pure substance. So we know that gasoline is a mixture, jelly beans in a jar mixture, soil is a mixture. So now we can go to the homogeneous part. Which one is homogeneous? Well, gasoline is a mixture of octane, which is a hydrocarbon, and usually now some ethanol. and maybe some other minor components. But they're uniformly distributed, and you have a homogeneous mixture. So gasoline is a homogeneous mixture. Jelly beans, not so much. You can tell by looking at the different colors that that mixture of jelly beans is not homogeneous. And you take my word for it, soil is not homogeneous. If you've dug down into the soil, you see variations in color, you see variations in particle size, um, and the structure of the soil varies as you descend through the various horizons also. So we only have one homogeneous mixture out of this selections. I mentioned physical change before, so we don't need to labor this one too much. The key here is chemical identity of the substance. If the substance remains unchanged in its identity, and those are characteristics that can vary from one substance to another, like boiling point, freezing point, reactivity, right? If it reacts a certain way with some other element or compound, then we can characterize its reactivity. And there are several other things. Elemental composition, for instance, those things do not change with a physical change. And there are various physical techniques that we can use to separate them. I mentioned distillation based on the boiling point, uh, filtration, chromatography. That's a topic that takes a lot of explaining. So if you want to know more about chromatography, you better go to a book and look it up. Chemical change, however, does change the identity of the substances. For instance, we put methane into a Bunsen burner, mixes with oxygen, then we light it, and the chemical reaction gives off heat, right? It's exothermic, and it produces out of methane and oxygen, it produces carbon dioxide and water. Those are distinctly different substances. Their identities have changed. And in order to do that, we have to break bonds between atoms and put them back in a different ratio. All right. So when we talk about compounds, where we have two or more different elements together, um, we talk about the bonds that hold them together. Those are known as intramolecular bonds. The bonds that hold a molecule together within the molecule. The intermolecular bonds are the forces responsible for those intermolecular bonds are between molecules, right? They hold molecules together in either a solid, a liquid, or a gaseous state. And those are the bonds that we weaken or break to go from one phase to the next. And we can classify those as either dipole-dipole bonds, where you have a permanent um, um, uneven distribution of electric charge in the molecule, and that will take some explaining also, so we're not going to dwell on that. It's just to recognize that some molecules have an uneven distribution of electrons or electric charge around the molecule. It's not a complete charge, right? We didn't transfer electrons, but it is a partial charge, and that allows molecules to orient themselves to negative side of one molecule, positive side of the other, and they have that attraction. Hydrogen bonding is a special case of the dipole-dipole force, and it's a much, much stronger. It is the strongest dipole force, and the best example of that is water, where you have oxygen and hydrogen bonded together. London dispersion forces are applied to all molecules, but they're most evident in molecules that don't have a dipole moment. Molecule like this, hydrogen and fluorine, that will have an uneven distribution, and it will be distributed in this direction as partially negative partially positive there. If you don't have different atoms pulling differently on electrons, like nitrogen, gaseous nitrogen is a bimolecular or binary uh, element, then there's no permanent charge there. So the only explanation we have for that is London dispersion forces. London dispersion forces are instantaneous and temporary, and they're based upon the uh, momentary redistribution of electrons around a compound. So just for an instant, we might have something like this. And then if we have a neighboring molecule, this negative will push negatives away and leave behind a positive. And the negatives will be over here. So once we have a negative and a positive, we can form temporary bonds. Those are London dispersion forces. Now, it's important to recognize that London dispersion forces are present in all molecules. All molecules have them. They're only evident when the other stronger forces are minor or non-existent. If you have dipole moments or hydrogen bonding, then London dispersion forces are so weak that they're insignificant. Now, which is stronger? Intramolecular, that is, holding an atom together, holding a molecule together, or intermolecular, between molecules? Well, the logical conclusion we should reach is that the intramolecular, holding the molecule together, those bonds are much stronger, and on average about 1% of the strength of a dipole-dipole. And there's a logical reason for that too. If, on the other hand, the intermolecular forces between molecules were stronger than the intramolecular forces holding a molecule together, then they would be strong enough to rip that molecule apart. It just wouldn't make any sense then, and we wouldn't have an ordered world anymore. All right, I mentioned those already. And relating these forces to phase changes, the let's see, yes, when we go from a solid to liquid, we're adding enough energy so that the molecules are moving enough to break those intermolecular forces that are holding the molecules together. Now, from a solid to a liquid, they're not completely broken. They're just weakened so that they can slide past one another. But when you go from a liquid to gas, those forces that we mentioned are broken, and they act as independent particles in the gas. The evidence for these intermolecular forces, one of the best evidences, not the only one, but melting points and boiling points. Right? If the temperature is if we got a certain temperature like 0 degrees, we have ice. Right? If we add energy and go past 0 degrees, we start melting the ice and we get water, because as the temperature increases, we're adding energy, we're adding heat, and that's breaking those forces. And a similar argument can be made for going from a liquid to a gas. One other thing we didn't mention about liquids and solids is compressibility. In other words, can you change the volume of a solid? Essentially, no. It doesn't matter how much pressure you put on the solid, it doesn't shrink in volume. Liquids, on the other hand, there's a little bit more space between the molecules, so you can push them closer together. But if you push them too close, then they're going to generate heat, and if you get rid of that heat, then you're going to turn it into a solid. So their compressibility is very low. We know that liquids can be compressed because it's been measured under high pressure, like water at the bottom of a 2-mile depth of ocean has been measured density, and the density is higher at 2 miles deep than it is at the surface. Another characteristic of liquids that is dependent upon these intermolecular forces is surface tension. Surface tension is simply the resistance of a liquid, that is, resistance by attractive forces, to an increase in its surface area. So liquids tend toward a sphere, which minimizes the surface area, right? And if you try to pull that surface area, make the surface area larger, there's a resistance to that. So for instance, if I take a pin, right, a sewing needle, and I very carefully lay it on top of a still pool of water, it will sit there. It will sit in the bottom of a trough, but it won't sink because the surface tension at the surface of the water, it has extra forces that are available being at the surface. And those forces are allowed to support the needle. Uh, Capillary action is another demonstration of these intermolecular forces. And it's actually a battle. Capillary is a narrow tube, and some liquids, when you put the end of the tube in the liquid, they rise up the tube to a certain height. And the narrower the tube, the higher they will go. There's a battle going on there, a balancing act between cohesive forces holding the molecules together and adhesive forces between the molecules of the liquid and the tubing. Those are adhesive forces. And we can see that evidence. Let's not use, well, we can use this one. If the meniscus is convex, then we know that the attraction between the liquid and the glass walls, those adhesive forces, are minimum. And the cohesive forces pulling that liquid together are dominant. Right? So the cohesive forces win in this case. And in fact, that liquid will not rise in the tube because the only way it can rise is if something is pulling it up. And those are the adhesive forces. Since they don't win, then this liquid will sit there in that tube at its level. And if there's nothing pulling it up, like if we don't create a vacuum above it, then it will sit there at the same level as the liquid outside the tube. On the other hand, if the adhesive forces are stronger than the cohesive forces, we get a convex meniscus. And this is characteristic of all water-based solutions inside a capillary or any type of glass container. You will see they form that concave meniscus. And by the way, if you ever are trying to measure some aqueous liquid inside a calibrated glass device, the calibration is for the bottom of the meniscus. The line where the bottom of the meniscus hits is your volume. It's not the middle, it's not the top, it's the bottom of the meniscus. So in this case, the adhesive forces win. Viscosity is another way to for evidence of these intermolecular forces. The stronger the intermolecular forces, the thicker the liquid is, the more viscous it is. Viscosity is a resistance to flow. So things like honey will flow very slowly. Things like water will flow faster. And that's an indication of their difference in intermolecular forces. Now, for the last two slides, I want to talk about what's actually happening in a phase change. For this diagram, this chart, we have temperature on the y-axis, and we're adding heat across this distance on the x-axis. So, as we add heat, the temperature of ice increases. We've still got solid. All the way up to 0 degrees, it's still solid, all of it. Once you reach 0 degrees, then we start to create liquid. We've weakened those bonds enough that now we have some liquid. We have solid and liquid together. Now the temperature is stable until all of the solid is gone, because the energy that's being put into it now is being used to break the bonds or weaken the bonds from solid into liquid. So the temperature is going to stay constant until you got all the solid converted into liquid, and then you get on this green track. Now we've got just liquid, and the temperature increases as we add heat until we get to producing steam or water vapor. And at that point, you have liquid water and gaseous water together simultaneously at 100 degrees until all the water's gone. Once all the water's gone, then the energy is added to the gas and the gas temperature increases. Okay? Another way to express this is using a phase diagram. This is a very simple phase diagram, in this case for carbon dioxide. Let's see. I don't have any more comments on that one, so I'll talk about it. What you'll note, if you ever see one of these phase diagrams, you'll notice that it has lines here. These are boundary lines between the phases, right? This boundary line here is between solid and liquid. Everything on this side is solid, everything on that side is liquid. Everything on this side is gas, everything on that side is liquid, and everything on this side is gas, and everything on this side is solid. Okay, those are phase boundary lines. And if you're on the line at any given temperature and pressure combination, you will have solid and liquid together on this line. Similarly, if you have a given pressure and temperature of a certain specific type and it falls on that line, you know that you will have liquid and gas together at the same time. And here you have solid and gas together under these conditions. Another, well, let's go to the one temperature and pressure combination where you have all three, solid, liquid, and gas, together at the same time. This is the triple point. Any temperature, any pressure outside of these two values, you will not have all three together. And the other point is when you go follow this liquid gas barrier up to a certain point, at that pressure and temperature combination, anything out here above this line or to the right of that line is going to be past the critical point. And in this region, we call this, whatever we have, is called a supercritical fluid. It's still a fluid, it flows, right? But it does not have a distinct liquid versus gas character. It's actually something in between.